Starting. Wonderful. So good morning, everybody. I hope you all have had a great weekend. And are looking forward to another wonderful day in fluids. Today, we're going to be mainly focusing on a discussion of shear stress and fluids and how it relates to friction. I'm hoping we'll get to the general discussion as well as a more in-depth look at friction and laminar flow. One thing I do want to say is, for the sake of mainly time and course pacing, I am going to bypass the discussion on microscopic momentum balances. You have the lecture as well as some examples in the course module. I will try to upload some solutions to those examples so you can get an idea of how Navier-Stokes and the Euler's equation is applied. But in my opinion, that level of analysis it's useful to kind of understand and know to a slight degree as an undergraduate, but the degree of complexity is such that I would expect that in terms of those that are more interested in microfluidics at a graduate level look at fluid mechanics. So before I kind of start jumping into the discussion of shear stress and friction and incompressible flow, are there any questions or points that I can clarify regarding momentum balances as we discussed it last Friday? All right, if not, then today we're going to be looking at friction and incompressible flow. So recall from a previous lecture, we had stated and defined a no-slip condition for flow, which means that high shear stress occurs at the fluid-solid interface. Meaning if I'm looking at flow through a pipe and I want to visualize that shear stress as a function of the radial direction, I would expect to see this level of shear stress in my system, where the shear stress is going to be greatest at the wall and decrease linearly in the radial direction, assuming my flow direction is occurring this way. So flow direction. Okay. And so the important thing to consider is this shear stress resists the flow, which results, or I can say resulting, in a reduction in energy of the fluid in the form of a pressure drop, which we also call friction losses or head loss. So, quick restatement of what I've just said. So when we're looking at flow through any sort of pipe or pipe section, or as it moves in general, the interfaces in which it's in contact with results in shear stress. That shear stress generates an energy loss, which we can measure, and which we as a function of a loss in pressure energy or a pressure drop. We can also call this skin friction. So the question then is, how can we show this loss using the mechanical energy balance? Well, if I were to pick some points in my system, now saying I have a P1 here, a P2 here, a velocity, height, the usual. And I'm going to pick points at 1, points at 2, and do a mechanical energy balance over those points. What I would have is something that looks like this. U2 squared over 2 plus P2 over rho plus G times Z2 equals U1 squared over 2 plus P1 over rho plus G times C1, which I also have to consider actually, so I'm going to shift this over, work in friction, work, friction. Sorry, I have to change. So in my drawing, I don't see any sort of pumps or turbines or anything, so there's not going to be any work. I'm going to say my heights are the same. There's no movements in static. And U1 and U2 are going to be the same. So U2 is equal to U1, Z2 is equal to Z1, and there's no work. So what I'm left with is simply an expression that says P2 over rho plus friction equals P1 over rho, or delta P over rho equals that friction, which we can also call delta PS over rho for skin friction. And so by looking at a mechanical energy balance between my 2 points, I can identify the emergence of skin friction within my system. But I just stated here a second ago that that is emerges due to the presence of shear stress. So if we recall from our momentum discussion, I had developed an expression that defines shear stress as a function of pipe diameter and pipe length. So go ahead, Blake. What did you say?
Was that supposed to be tau?
Yes, it's tau sub W. It defines the shear stress that occurs primarily at the wall or the fluid wall interface. And so when we did a momentum balance over the flow through a pipe, this was the expression we had that relates pressure drop and shear stress.
Dr. Lopez, is that a 4 in the denominator?
Yes, it is. It's
You.
pressure drop times the diameter of the pipe divided by 4 times the length of the pipe. So rearranging for pressure drop, I get an expression that looks like this: 4 times the pipe length times the shear stress divided by the diameter, which, while nice, leaves us with an issue. And for record, this is equation 5.5 at page 100 of your text. So what it tells us is if we know pressure drop, we can determine shear stress. Or vice versa. However, more often than not, what we're really looking for is a way to estimate pressure drop within our fluid systems. We want to have an idea of what are the losses that we should expect and moving a fluid from point A to point B so that we know how much energy to put into the system to have sufficient transport within our systems. And so a more useful variation is needed. And so what we do, once we're engineers, we developed our own variable, which is known as a friction factor. To describe the expected losses as a function of shear stress and the kinetic energy of a fluid. As these two forms are the most predominant variables which describe friction factor that we see within fluid systems. And so we've defined our friction factor, which I denote as lowercase f, like this, as tau w divided by rho u squared over 2, which is a little easier to see as 2 times tau w, which is the shear stress, divided by rho u squared. And so now what we have is this new variable, friction factor, which relates to shear stress, as well as our pressure drop expression here, which relates to shear stress. So if I can combine these two expressions, what I'm left with is F equals 2 tau w over rho u squared, which tau, once again, is delta P times diameter over 4 times L. So I have 2 over rho u squared times delta P times diameter over 4 times L, which if I combine this, what I'm left with is delta P times diameter over 2 rho u squared L. And if I want to solve for my pressure drop, I'm left with delta P equals 2 F rho u squared L over D. Now this is the pressure drop as a function of that shear stress, or that pressure drop by skin friction. So I'm going to go ahead and just designate it as delta P as an S. A lot of times what you might be looking for in your system is a delta P over rho, because units in your energy balance. So that's just simply 2 times F u squared L over D. Or we may be interested in knowing the pressure drop due to skin friction per unit length. which is 2F rho U squared over D. Each of these forms of the expression is equally important. And so I'm going to do my fanfare so that you kind of get the idea that these are some key expressions that you're going to want to know in terms of how we can define pressure drop as a function of that friction that occurs due to shear stress. Do you guys understand and follow how I was able to derive that expression?
Yes.
All right. So let's take a look at an example, which is here. Determine the pressure drop per unit length of pipe, which we can do it in, let's say, PSI per foot for ethanol with a specific gravity of 0.79, flowing at 10 feet per second through a 3-inch Schedule 40 pipe. We're keeping in mind it's a 3-inch Schedule 40 pipe, so the inner diameter is actually going to be 3.068 inches, and the friction factor provided as 0.005. So I'm going to throw you guys in breakout rooms, give you 3 or 4 minutes to work on this in groups, and then we'll discuss it. Good way to kind of get the brain moving first thing in the morning.
So Dr. Lopez,
Yes.
I assumed that S he gave us was supposed to be specific gravity. Was that accurate?
Yes, it was.
Okay.
Yeah, I'm pretty sure I denoted it as S sub. Yes, yeah. Yeah, usually when I say S, it's specific gravity. But like I said, I completely understand with the alphabet soup.
Yeah, it can be a little confusing sometimes.
So how did you guys do?
I had an answer.
All right, did your group got an answer?
Yeah,
What was your answer?
I got 192.83 pound force.
We're looking for a pressure drop per unit length. And that seems pretty high for this one.
I got a 1.34 psi per foot.
Okay, that's closer. What other groups? What else did you guys get? Right, so we're going to be using this form of the expression. Delta P over L is equal to 2 times F times density times velocity squared over the diameter. The diameter was 3.068 inches. F provided was 0.005. Rho was the specific gravity times the reference, which we use water when we're looking at ethanol, so 0.79 times 62.4 pound mass per cubic foot, which 0.79 times 62.4, 49.3 pound mass per cubic foot. D, we already said D. So, and the velocity provided was what, 10 feet per second. So since we're looking for pressure drop over unit length, we just need these values. So if we plug all this in, 0.005. Now the friction factor is unitless, so keep that in mind. So then we have our 49.3 pound mass per cubic foot times our 10 feet per second squared divided by the diameter, which was 3.068 over 12 feet. So if we do this, we're left with, I believe, it's pound mass per feet squared per second squared, which means we need to add our G sub C to get it into pound force. So we divide by 32.2 pound mass foot per pound force second squared. And we also have to change one of those feet that we end up with, our feet squared to inches squared to get PSI. So 1 foot squared is 144 square inches. So if we do all that, the units cancel and we're left with pound force per inches squared per foot, or PSI per foot. And we should have a final solution of about 0.042 PSI per foot. So I'm guessing you were all on the right track. It was most likely just the units and making sure, like I said, the G sub C and especially the 144, it's always tricky to try to remember when those need to come into play. Is there any questions or things I can clarify on that example problem? If not, let's take a look at one more thing.
Okay, I'm mad. I'm gonna use trash. Oh, sorry.
So let's take a look at this question and talk about it for a second. So the question asks, in general, increasing the Reynolds number decreases the friction factor for a given fluid traveling in a pipe. So you guys think it's true, false, true for laminar flow, or true for turbulent flow? What do you guys think on this question?
I
Any
think
idea?
it's true.
Think it's true? Any
Yes.
other? I got a true for laminar flow from somebody. I appreciate the participation. All right, everybody's gonna say C, true for laminar flow. No, oh, I got one A, another true. All right, so this one's interesting. The answer is A. However, it's interesting like how I've written it, because while the friction factor value will decrease as a function of Reynolds, the friction itself will increase, or the actual energy dissipation will increase with increasing Reynolds number. And so to understand that concept, let's take a look how friction applies, specifically when we're looking at laminar and turbulent flow. We'll probably get through a discussion on laminar flow today, and we'll finish up our discussion on turbulent flow on Wednesday. But I will say, for note purposes, in general, because everything depends, increasing our Reynolds numbers results in a decrease of our friction factor. However, the frictional dissipation what I mean by that, the actual energy loss, will increase with increasing Reynolds number. So, like I said, let's look a little more closely now, focusing on friction.
Is there any chance you could scroll up for just a second?
Of course, and I can zoom out. I'm happy to move however you guys need. Friction and laminar flow. All right, I'll give a little pause because, like I said, I have a tendency to move a little quickly, and I don't want to leave anybody behind. So, if you can recall from our previous discussions of laminar flow, as well as from discussions I'm sure you've had in transport, laminar flow has a parabolic velocity profile. Where if we use our wonderful flow through a pipe, even though it looks like a road, the velocity visualized follows this parabolic profile, with the maximum velocity occurs at the center. So Umax occurs at center of pipe. And we also recall when we discussed friction and shear that the shear stress for laminar flow follows this form for Newtonian fluids, where the shear stress can be a function of the velocity gradient as a function of the radial distance, as well as the viscosity. And since we're looking at Newtonian fluids, that dependence on viscosity, or the viscosity, isn't going to change as a function of that velocity gradient. And so what that means is, if we look at a thin ring within a pipe, I can say the surface area of that thin ring follows this form, 2 pi r dr, when we're looking at the circumference as a function of that radial distance. So we can write the function, or that velocity gradient now, instead of looking at it simply in terms of a y, we're looking at it in the radial distance. Looks something like this. Where we have our velocity gradient in the radial direction, where tau w is the shear stress at the wall, rw is the full radius of the system, or the radius from the center of the pipe to the wall, which we would just call r, and r is essentially looking at any slice in between. So we can integrate this from 0 to w, or u, and from the wall to the center. And what we can find is that the velocity is directly related to the shear stress divided by 2 times that full length times viscosity times the difference of the squares between the full length radius as well as that given distance between the center of the pipe. And so when we're looking at the center where Umax occurs, r equals 0. And so we find that Umax is simply tau w rw over 2 mu. And to be honest, you don't have to write all this down. There is a point to all this. I just like doing this discussion and derivation because it helps bring what we get to in context. And so I'll take a step back. So looking at the velocity profile as well as our description of shear stress as a function of that velocity gradient we see in laminar flow, we can set up an integration for that velocity gradient, solve it in terms of the velocity, and then what we're going to look at now is a comparison between the velocity at any point along the radius as compared to the maximum. So if I take u over u max, what I'm left with is 1 minus r over rw squared, which gives us our parabolic profile. However, we can quantify things or our behavior in terms of our average velocity or mean velocity. So I've stated previously that more often than not, we consider the average and mean to describe the general behavior that we see. And what we find is that the average velocity compared to the maximum velocity is simply 1/2, meaning the average velocity is half of the maximum that we see. So that if we're going to look at that maximum velocity, U max as a function of shear stress, that tells us that the average velocity as a function of shear stress is just tau W RW over 4 times viscosity. So what can we do with this? Now we have a function in laminar flow of our average or mean velocity as a function of shear stress and the radius of the wall. Well, if we remember from earlier, we also just said that for flow, now is delta P over diameter times 4 times length. Did we not? So now I have another expression for shear stress that I can compare with this velocity expression. And so if I plug in shear stress here, I have U bar equals delta P times diameter over 4L times our discussion that we see for applies to laminar divided by 4 times mu. Now the problem here is we have a radius and a diameter. Now for all intents and purposes, the diameter is just 2 times the radius. Which means that if I'm going to plug in for radius, I just need to plug in diameter over 2. So if I plug that in, I have delta P times d squared divided by 32 mu L is equal to my velocity. So now if I want to solve for pressure drop, in laminar flow, I just rearrange the expression. I have delta P is equal to 32 U mu L over d squared. And this expression is important as it denotes what we expect to see in terms of skin friction, particularly as it applies to pressure drop and laminar flow, such that it has its own name, which we simply call the Hagen-Poiseuille equation. And one thing you want to notice, the skin friction or pressure drop that we see in laminar flow is not only related to velocity, but it's also directly related to fluid viscosity. And this is something that we'll see in laminar flow, but we will not see in turbulent flow, primarily the existence of the viscosity term in our expression for pressure drop. Any points of clarification I can make and how I was able to essentially derive this Hagen-Poiseuille expression by looking at flow through a pipe, particularly laminar flow, and building off our previous expressions that we had discussed in laminar flow as it related to both flow and shear. And like I said, I'm not expecting you to do any sort of crazy derivations in this class. I think this is one of the derivations where I think it's kind of neat, for lack of a better term, to see kind of how this this mathematics comes to be. So the last question that I want to answer in terms of laminar flow is, how does our friction factor influence our analysis of friction in laminar flow? Well, if we recall from earlier, we had defined our friction factor F as what? Let me grab my notes, take a quick look. Of course, it's the page that's way at the bottom. Oh, here it is. 2 tau W over rho U squared. So if we go back a minute and we take a look at our expression that we had for velocity as a function of shear stress, this U equals tau W RW, which I'm just going to call D over 2. So it would be 8 mu. And we can combine these two to eliminate the shear stress. We have F is equal to 2 over rho U squared times 8 U mu divided by D. Does everyone follow that? So with this, one of my velocities cancels. So I'm left with 16 mu over rho U D. Now, what does this look like?
That's Reynolds number.
That's the Reynolds number, yes. So for laminar flow, our friction factor is simply 16 divided by the Reynolds number. So hopefully you guys are starting to see how looking at derivations for shear stress from different angles allows us to essentially remove that value from our expressions because we really can't measure it very well. Because at the end of the day, when we're engineers, we want to be able to do calculations and make predictions based on data we can obtain, which means we need variables that can be measured easily when we're looking at any sort of system in operation. Well, I can measure density, the flow diameter, viscosity, and velocity pretty easily. You know, these are those variables that we can determine without too much headache. And so that's the key motivation for eliminating our shear stress, even though at the end of the day, it's what's the primary driver for the friction that we see in our flow systems. We have to eliminate it because we simply, there's no easy way to measure it. But we can measure other things that are directly related to it. And so what we're left with is this value here, where if we're interested in friction or pressure drop and laminar flow, we can rely on the Hagen-Poiseuille equation, or if we're interested in using an analysis via the friction factor, we can solve for our friction factor as simply 16 divided by the Reynolds number. All right, so we got about 5 minutes. The last thing I want to look at is this example here, which is an exploration of looking at another pressure drop per unit length. This time, let's assume that their flow is laminar. Well, so we have pressure drop per unit length, fluid flowing through a 2-inch pipe at 1/2 foot per second if the viscosity is 1.2 times 10 to the minus 2 pound mass per foot second, and the fluid density is 36.2 pound mass per cubic foot. And the question asks, how does the pressure drop per unit length change if we increase the fluid velocity by what to 1 foot per second and 2 feet per second? All right. So, like I said, we'll wrap up. For the sake of time, I'll just kind of walk you all through it. So for this system, we're looking at pressure drop per unit length. So delta P over L is going to be 32 mu U over D squared, rearranging the Hagen-Poiseuille expression. So we have 32. The viscosity as provided in the problem was 1.2 times 10 to the minus 2 pound mass per foot second. The velocity was 1/2 feet per second, and the diameter was 2/12 feet. And since we're looking at English units, we have to add in G sub C, 32.2 pound mass feet per pound force second squared, and then convert from inches squared or feet squared to inches squared. If we put this value in, we should be left with approximately 1.5 times 10 to the minus 3 PSI per foot. All right, now that, like I said, to wrap up, since that one was just kind of number crunching, what do we expect to happen to our pressure drop per unit length if I double the velocity?
We would double.
It would double, right? So based on the Hagen-Purcell expression, it would double. So I expect about 3 times 10 to the minus 3 PSI per foot when U is 1 foot per second. And likewise, if U is 2 feet per second, my pressure drop would go to approximately 6 times 10 to the minus 3 PSI per foot when U is equal to 2 feet per second. Now keep in mind, this is only true when we're looking at laminar flow. This analysis is going to change dramatically when we consider turbulent flow. But like I said, I think we're right out of time, and this is a really good place to stop. So I think on Wednesday we'll jump in and now analyze these same systems, but from the perspective of turbulent flow. Any questions or things I can answer? Hopefully you guys kind of follow along without too much difficulty. I thank you all for your attention and attending class. And as always, if you guys need anything, feel free to reach out to me. And if you don't hear back from me in a timely manner, I don't mind if you just send me follow-ups. I understand. But if not, thank you all. Have a great day, and I will see you all on Wednesday.
Will you be on office hours at 11?
I will be at office hours at 11, yes.
Okay.
Thank you.
Thanks.
Of course.
Thank you.
Thank
All
you.
right, guys. Take care.
you.